All right, good. So, yes, we're talking about section 5.5 today. This is triple integrals in cylindrical and spherical coordinates. All right, so we talked about triple integrals, but we were using, in section 5.4, we were using Cartesian coordinates. This is just x, y, and z. And that's a rectangular coordinate system. So what we're going to do is we've talked about polar coordinates already. And those are that's a two-dimensional coordinate system. But since we've moved into 3D now, we're doing triple integrals, we need to talk about kind of the analogies of polar coordinates, but in 3 dimensions. And it turns out there's more than one way to do this. There's cylindrical coordinates is one generalization, and spherical coordinates is another one. And they both have their applications. They're both useful in different contexts. So we're going to talk about cylindrical first, and then we'll talk about spherical. And then we'll look at some integrals that are where those can be used to evaluate those integrals. All right, so let me switch to the doc cam here. Okay, you should be seeing the paper. Okay, so triple integrals in cylindrical and spherical coordinates. Let me just review what happened with polar coordinates. So a review of polar. Okay, when we dealt with polar coordinates, we said that we can convert from Cartesian to polar with these two equations, right? We had x, our Cartesian coordinate, our first Cartesian coordinate, and y, our second one. These relate to polar coordinates via these two equations. X equals r cosine theta, and y equals r sine theta. And what polar coordinates do is they take these rectangular coordinates and they specify a different way to identify points in space. So if I have this point, the rectangular coordinates would just be x comma y. Polar coordinates, and that's the distance in the x direction and the distance in the y direction. Polar coordinates specify this point by specifying an angle from the x-axis, that's called theta, and a distance from the origin, that's called r. So in polar coordinates, this point would be given coordinates r comma theta instead of x comma y. So you're given a distance and an angle, and that tells you where you are in space. Right? And that's how polar coordinates work. And we can convert from Cartesian to polar using these formulas. Okay? So when we move into 3 dimensions, we're going to add another axis here, and we need to extend things out into that other dimension. All right? And so let's talk about the first way to do that is cylindrical coordinates. So cylindrical coordinates are probably the most basic way to do this. All we're going to do is we're just going to add that z coordinate into the mix. So really, it's almost doing nothing. So the relationships are the same for polar. We're going to do, oh, that's a sine theta, y equals r sine theta. And then how do I convert the z? Well, I just leave it the same. Okay, so in cylindrical coordinates, we just add the z variable to the z coordinate to polar coordinates. That's all it is, polar coordinates plus the z. So how is that going to look in 3 dimensions? Well, I have my x, y, and z axes. I've got the setup for polar coordinates in the xy plane. So if I specify a point in space, what I'm going to do is I'm going to drop it down to the xy plane and look at that point down there. And then that point I can specify using these this r and this theta. So r measures the distance that I am from the origin. Theta, as before, measures the angle from the positive x-axis. And then z is going to be this coordinate here, how high I am. The same z that we had in Cartesian coordinates before. All right, so the coordinates are going to be r, theta, z. And that's going to specify a point in space using these cylindrical coordinates. So we're going to specify how much we have to spin around in the xy plane, how far we have to go out, and then how high we have to go. And that will tell us where that point is. Let me go to, just to make sure that we've got this down, I want to just show a three-dimensional view of this with my browser, which, as I said, is struggling at the moment because I've got a lot of things open in 3D ready to go. Hopefully it works. Maybe I have to hit the reload button. So you should be seeing my browser. Let me know if not. And please, if you can, let me know using the voice. Unmute yourself and let me know, because for some reason when I switch to sharing my screen like this, I can no longer see the text chat. Okay, it's loading and it's having a hard time. Let's give it a second. There we are. Okay, cool. Okay, now I need to push a button on here, but it's covered up by all these controls I have on my screen. Looks like it's still loading. Okay, here we go. Is this gonna work? Okay, so hopefully you can still see this. This is the setup for cylindrical coordinates. So you can see that on the right-hand side here, we have the picture of just in the XY plane. And so if I change theta, you can see that I'm changing the angle in the XY plane of the point that I'm talking about, right? And if I change r, I'm changing the distance that the point is from the origin. And then z just moves me up and down. So now look at the view on the left here. Z is telling me how high or how low I am. If z is negative, I'm below the XY plane. If z is positive, I'm above. So this is how you can specify points using these cylindrical coordinates. Changing r, changing theta, and changing z will get you anywhere in three-dimensional space. All right. So, all right. So let's go back. One thing we have to talk about is if we're going to do integrals using cylindrical coordinates, we're going to have to know what that volume element is. So let's talk about that. We'll talk about the volume element. Well, recall what the area element was in polar coordinates. When we do an integral, a double integral, we write a dA at the end, right? So, so in 2D, we do a double integral over a region, and we have some function in here, and then we write dA. That's the area element, okay? And what that's representing is an infinitesimally small chunk of area. And the integral, what it does is it multiplies that by the function and then adds up all those values. So you end up getting, when you integrate a function like this, you end up getting the volume underneath the function because you're multiplying the height of the function times the area, and that gives you a volume under the function. But we need to talk about what this area element is, and we talked about that. If we imagine a small change in theta, so maybe I go from theta is this to theta is this. Right? That's not bad, that's small, but I have to expand it just so that we can kind of see it clearly. And then imagine a small change in r. So let's say we go from r equals here to r equals here. Again, not that small, but I need to draw it large so that we can see what we're talking about. Then what I get is I get a wedge, right? So the distance in this direction is what we call a small change in r, that's dr. And naively, you might first think, oh, well, then the distance in this direction is d theta. Well, that doesn't quite work because you'll notice it's different here than here. It's actually the distance in this direction depends on r. And we talked about how we have to use the formula for arc length to get this distance. And the formula for arc length is very simple. The length of an arc on a circle is just r times theta, if theta is measured in radians. And so since the distance here in theta, not the distance, but the amount of change in theta is d theta, I'm going to multiply r times d theta. And that's how I get this distance. That's r d theta. So this little chunk of area here, which we're calling dA, is approximately equal to this distance times this distance. So it's dr times r d theta. So dA is, and if you multiply that, you can put the r out front, is r dr d theta. That's usually how we write it. But you could write it r d theta dr, that's fine. But we usually write it this way, put the r's together. Right? And that's how we get our area element. So that's the area element. So we want to get the volume element for cylindrical coordinates. What are we going to do? Well, we're going to take this picture and we're just going to extend it into the third dimension. All right, and we're just going to add a dz to it. So what does that end up looking like? Well, so in 3D, for the cylindrical coordinates, this was for the polar coordinates. This was just polar. This will be cylindrical. Moving to 3D, we're just going to take this picture and we're going to add that z direction. So yeah, I guess let's just draw that whole thing out here. All right, x, y, z. So the same picture. So what we did is we took a change in theta, we took a change in r, right, and that gave us this wedge shape down here. And now we'll just extend it into the z direction. So we'll just lift that up, and you get this wedge that's extended in the z direction. So now we have dr takes us this way. R d theta gets us that dimension. And then this is just simply dz. So if I want the volume, I just multiply. This times this gives me the area, multiplied by the height gives me the volume. So dv, this is the punchline here, it's going to be the product of all these. So I'm going to have r dr d theta dz. So that is what we're going to use when we do integrals in cylindrical coordinates. It's pretty straightforward extension of polar coordinates. We're just throwing the dz on the end. Yeah, that's in effect all that ends up happening. Okay, so let's look at an example where we have to do an integral in cylindrical coordinates. Okay, so what we're going to do is we're going to evaluate this triple integral over a region. We're going to integrate xz dv, so with respect to volume. Whenever you see three integral signs, it's going to be dv. If there's two integrals, you're going to have dA. And then we'll later break that down into the dx's and dy's, or the dr's and d thetas. All right, but I need to tell you what the region is that we're integrating over. All right, so R is going to be the set of all points x, y, z, such that x squared plus y squared is less than or equal to 9. X is greater than or equal to 0. Y is greater than or equal to 0. And z is between 0 and 1. So what are we dealing with here? Well, when I see x squared plus y squared, I know that if this was x squared plus y squared equals 9, that would be the equation of a circle of radius 3, right? And that tells me right there that maybe cylindrical coordinates are the way to go, because cylindrical coordinates deal with, they're kind of circular in their nature, right? They have that radial, they have that angle as part of it. And so it's natural to write down circles in cylindrical coordinates. It's very easy. So this tells me that maybe I should be thinking of using cylindrical coordinates right here. So what we're going to do is we're going to convert everything to cylindrical. All right, so remember our formulas. X equals r cosine theta, y equals r sine theta, and z is just going to stay z. Okay, so what does this thing become? Well, then xz, our integrand, that's what we call the thing that we're integrating, is going to become r cosine theta times, well, z stays z, so it's just z. Okay, so that's what this thing is going to become. So in our integral down here, we're going to have, let's put, yeah, I guess that's fine. We'll just leave it like this. R cosine theta times z. All right. And now the dv. We should probably figure out what these things look like before we write down the r, dr, d theta, dz here, because sometimes we have to, as we saw in the last chapter, we have to reorganize those things. We have to write them in a different order. So we have to be careful about the order in which we integrate. So let's figure out what this region looks like. Here we have, we said that x squared plus y squared equals 9 is a circle. So if I'm saying that it's less than or equal to 9, we're inside the circle. It's actually a disk. It's the interior of a circle of radius 3. Now, what does x squared plus y squared become when we use these coordinates? Well, x squared plus y squared is the same as r squared cosine squared theta plus r squared sine squared theta. I can factor out the r squared. And cosine squared plus sine squared we know is always equal to 1, right? So this is just r squared. So that's very nice. This just becomes r squared is less than or equal to 9. Or in other words, r is less than or equal to 3. So that is a good thing to recognize. This just becomes that. R is less than or equal to 3. Now, to say that x is greater than 0 and y is greater than 0, let's not substitute those in. Let's just think about that. We'll get back to that in a little bit. The z, well, z is z, so I don't need to even, I guess that part's, you know, z is just the z coordinate in cylindrical coordinates, so that's fine. Let's think about what this is saying. Let's draw the picture of what we're looking at here. X, Y, Z. Okay. R is less than or equal to 3. So we're inside, let me draw in a dashed line, the circle of radius 3. All right. We're inside this circle. That's what this is telling us. X is greater than 0 tells us that we are up here. We're in this part. We're at the positive x-axis. So we can ignore this back side of the circle, right? So we're really only looking at this front part up here. Those points in the back are not part of the region. And then what else do we have? We have y is greater than 0, greater than or equal to 0. So that means we can ignore this half of the circle over here where the negative y's live. So really all we're left with is just this part of the circle. And remember, r is less than or equal to 3, so we're actually inside the circle here. So we're actually in there. And then finally, z is going from 0 to 1. So we're going to start down here at 0, and we're going to go up to 1 on the z-axis. Right, so just lift all that up. This is the region that we're dealing with. Okay. Well, so now let's see. We need to think about what this is in cylindrical coordinates. Well, r is going from 0 to 3. What's theta going from? Well, remember, theta starts here at the positive x-axis and then winds around counterclockwise. So we're going from theta equals 0 to here. That's 90 degrees. That's pi over 2 radians. So we see that theta here is going from 0 to pi over 2. Okay. And we were told, let me write down again the r. R is going from 0 to 3. And z is going from 0 to 1. Well, that's very simple, isn't it? Right? These are going to be our bounds here. Since these are all constants, it doesn't matter what order I write the dr, the d theta, and the dz. Okay? So let's put that volume element in here. So here's our volume element. We know that it's equal to r dr d theta dz. And like I said, I can write it dr d theta dz. I could even mix these up. I could write these in a different order. It's not going to matter. Now I put the bounds in. First integral on the inside is r. R, we said, went from 0 to 3. So here we are, 0 to 3. The next integral we do is theta. Theta, we said, went from 0 to pi over 2. So here we are, 0 pi over 2. The third integral is with respect to z. We said z went from 0 to 1. So there we are, 0 to 1. So that's what we've got. I could write this integrand here as r squared cosine theta is z. So let's think about it that way, since we have two r's in there. All right. Any questions so far? Go ahead and let me know. I'll keep going, but I'll keep my eye on the chat. Okay. So now we have to do this integral. So first we're integrating with respect to r. So we're going to anti-differentiate r squared. We're treating theta and z as constants. So the antiderivative of r squared is 1/3 r cubed, right? So 1/3 r cubed cosine theta z. We're going to evaluate that from 0 to 3. And then we're going to integrate that answer according to what we had out there. Well, let's see. When r is 3, I get, I goofed. You were probably about to say something. Antiderivative of r squared is 1/3 r cubed. Right? Okay. So when I plug in the 3, I get 27 divided by 3 is 9. When I plug in 0, I just get 0. So this thing is just 9 cosine theta times z. Okay, so moving along. Now we do the antiderivative with respect to theta. Antiderivative of cosine theta is sine theta. So what we have here is 9 sine theta times z evaluated from 0 to pi over 2. And then we'll integrate that when we're done evaluating it. When theta is pi over 2, sine of pi over 2 is 1. When theta is 0, sine of 0 is 0. So I'm going to take what I get when I plug in 1 up here and subtract 0. So that's just, I just get 9z. Okay, finally, we do this integral. Antiderivative is 9 over 2z squared. Right. Evaluated from 0 to 1, we get 9/2. And so there's our final answer. Okay, so in these problems, you're going to have to, when you convert, you have to convert the function that's the integrand using those formulas that we wrote down, these right here. So we converted the xz in terms of r, theta, and z. We wrote that down. We also have to interpret our region in terms of cylindrical coordinates. Sometimes it'll be given to you in cylindrical coordinates to begin with. Sometimes, like this one, it'll be given in Cartesian, and you got to think about, all right, well, how do I think of that in cylindrical coordinates? And one of the things that I like about this example is that you notice we plugged these equations here into some of the inequalities here, but not all of them, right? Sometimes you just by knowing x, just by knowing what this means in the picture, x is greater than or equal to 0, y is greater than or equal to 0, we can tell what theta is going to be. I don't have to plug in this stuff into these inequalities. So don't go crazy and just plug everything into everywhere. That may not be the slickest way to do it. Proceed carefully, all right? But if you do see something like this, x squared plus y squared, certainly that should suggest something nice is going to happen involving cylindrical coordinates. Okay. So I would just do one of these at a time. Just do this one and see if that's enough to figure out what the region is. Draw a picture and then go from there. If it's not enough, then maybe make some more substitutions. Okay, any questions? Okay, so let's do something. Let's find the, let's do a problem where we find the volume of a cone. Okay, you might know the formula for a cone. It's in the back of most people's Calc 1 book, so it's something they let you know about. But how do they get the volume of a cone? How do you actually deduce that? So let's find the volume of let's see, how should I write this down? Yeah, let's say the radius and the height are the same for this one. All right. So let's find the volume of a cone. So we'll start simple here. Volume of a cone with height and radius equal to, let's not do 1, let's do something more interesting like 2. Okay. All right. Now we're dealing with cylindrical coordinates, so maybe we can use these to get a handle on this. Let me draw a picture of it, and I'm going to draw a picture of it. I'm going to draw a picture of it upside down. You don't have to do it this way, but I think it'll end up being easier if we do it this way. So here we have our cone. I'm going to put it centered right on the z-axis there. And the radius is going to be 2, and the height is 2, so this number is 2. Okay. So how do we get that volume? Well, what I'd like to do is find out what this region is in terms of cylindrical coordinates. Okay. So let's see here. If I want to get this diagonal line, well, here what I'm looking at, and as I'm looking in the, well, this is the z-axis, and if I just restrict myself to the yz plane, I'm just getting a diagonal line, right? And in fact, that's the equation z equals y. Okay, but in this plane, that's also, well, if I'm restricting myself to this plane, y is the same as r here. Right? Because r is just the distance from the z-axis. And in this plane, so is y. So you can see that this line here is really given by z equals r. The height of this line is the same as the distance that line is from the z-axis. And I could have done the same thing on the x-axis. Right? That line coming out this way, when I restrict myself to the xz plane, x is the same as r. Right? The r is just the distance in that direction, and so is x. And so again, this line is just z equals r. And I think you can tell that as I spin around the cone is really given by the equation z equals r in any direction. If I just go out some distance in the r direction and go an equal distance up, if I make my z equal to r, I will land somewhere on this cone. Right? So the equation of this cone really is just very simple. It's just z equals r. Okay, so I think that's enough to figure this out. All right, so if we want to find the volume of something, remember what we do. We take the triple integral of 1 dv. That's going to be the volume. Okay, and so our region here is just that cone. All right, so let's figure out what these bounds are going to be. Let's set this up. R, dr, d theta, dz. Okay. What does r range from? Well, r starts at 0 and comes out until we hit the cone, right? But as we said, the cone is given by z equals r. So r goes from 0 to z. Okay. Whatever my height was, that's exactly how far I have to go out until I get to the cone. So r is going to span this entire distance here. What about my theta? Well, theta is how far I go around. Well, look, I went all the way around. I got a circle here. The top of the cone is a circle. So if I was doing half the cone, I would just do theta from 0 to pi. But I'm doing the whole cone, so I go from 0 all the way to 2 pi. And then what does z do? Well, the height of the cone is 2, so z goes from 0 to 2. Right, and that'll do it. So let's see what this comes out to be. I anti-differentiate this with respect to r, I get r. Evaluate from 0 to z, I get z, right? So this just becomes z. Oops, okay, hold on. I forgot about my r over here, right? It's not 1, it's 1 times r. So the this is an r, that simplifies to r. So the antiderivative is 1/2 r squared. Okay, I thought that was gonna be too easy. So I evaluate that from 0 to z, I get 1/2 z squared. Okay. Almost forgot about that r. It's easy to do that, so be very careful about that. Now I anti-differentiate this with respect to theta. Well, that's just 1/2 z squared times theta. Evaluate that from 0 to 2 pi. It's just, you just multiply this by 2 pi, right? Because it doesn't depend on theta. So it's just pi z squared. Okay, now in the last part, we're just anti-differentiating with respect to z. So that's 1/3 z cubed, right? Evaluated from 0 to 2. So that is pi over 3. 2 cubed is 8. And so, and then evaluated 0, you get 0. So this is just 8 pi over 3. I didn't write the evaluations as I did in the last problem. I'm trying to save a little bit of space here. You can fill in the details on your own. I want to point out, though, that we could have done this a slightly different way. We didn't have to do dr, d theta, dz. You could have done dz, d theta, dr, or actually dz, dr, d theta. Either one of those would work. Let's do let's do this integral dz. Let's really mix it up. Let's do dz, dr, d theta. Okay, how would I set it up this way? Well, here, my first integral on the inside is a z. So I'm asking, what does z go from and to? Well, let's look at the picture. Z doesn't start at 0, right? That's outside the cone. I'm not at the cone yet. I'm going up and up and up and up and up and up and up until I hit the cone. Now, at that point, z is equal to r. So z starts at r. And then how high does z go? Well, z goes as high as 2, right? It goes to the top of this cone. So if I set the integral up this way, I would go from r to 2. Okay. Now, what does r go from? R starts at the center and goes all the way out to the edge of the cone, right? I'm gonna do that, go from r to 2 for every r from here all the way out to the perimeter, right? So if I'm at the center, z is going to go from 0 to 2, right? If I'm halfway out, z is going to go from here to 2. If I'm all the way out, z is going to go from 2 to 2. All right, so r goes from 0 to 2. And then theta, as before, takes me all the way around the cone. So it goes from 0 to 2 pi. So notice it looks a little bit different, but this is how you'd set it up if you reversed the dz and the dr. Okay. And go ahead and work it out. Make sure, homework exercise there, just to verify on your own. Make sure, see if make sure it also gets you to 8 pi over 3. It should. Okay. All right. Any questions on that one? Okay, so that's it for cylindrical coordinates. So what we're going to do next is spherical coordinates. This is another way to extend the idea of polar coordinates into 3 dimensions. Okay, so this is the same section, this is just a different part of the same section. Spherical coordinates. Okay. So the way spherical coordinates work, I think it's hard for me to draw this on a flat sheet of paper, so let me take you to the computer here, and we'll look at it over there. So let's go. To my browser. And I gotta reload this page. It may take a little while. Oh boy, that's not being friendly, is it? Let me just try that again. Let me try accessing this different way here. I don't know why this is getting so sluggish. I don't know what the issue is here. Okay, this is working now in this other tab. Kind of. All right. Yeah, okay. So can I get this in full screen? Hopefully you're seeing that like I am. I don't know. So on the right-hand side, you should see something that looks just like polar coordinates, right? And on the left-hand side, you should see the three-dimensional view, okay? Let me know if you're seeing something else. So what we're gonna do to specify a point in space here is we're gonna use the polar coordinates on the base, or almost. We're gonna use this theta, all right? So theta is gonna specify our angle from the x-axis, just like polar coordinates. So that's gonna swing us around from the positive x-axis, all right? Now, to get up away from, to tell us how far out into space we are going to use another angle. And that angle is going to be measured from the positive z-axis. And that angle is called phi, P-H-I. P-H-I, that's phi. And phi is going to measure the angle from the z-axis. So see, as I change phi, you can see that that angle changes. And so phi, when it's 0, we're at the z-axis. And as phi increases, I come down from the z-axis, and as phi goes greater than 90 degrees, or pi over 2, I go below the xy plane, right? So phi here is measuring my angle from the positive z-axis. Theta is my angle from the positive x-axis. And now one final coordinate is rho. That's spelled R-H-O. And that's kind of like R, except instead of measuring the distance from the z-axis, it measures my distance from the origin. So notice as I change rho, it actually takes me to and from the origin. When rho is negative, I go to the other side. Right? So by adjusting theta and phi and rho, my distance from the origin this time, I can specify any point in space. So these are spherical coordinates, okay? Okay. So what we need to talk about is how to convert from spherical to, we need to talk about how to convert from spherical, from Cartesian to spherical. And so we'll write down some formulas there. And then we will talk about the volume element in spherical coordinates. And then we'll do some triple integrals in spherical coordinates. All right, so we'll go down to the sheet and we'll take a look. All right. Let me try to motivate how these equations are going to come about. I'll do the best I can drawing in 3D on this two-dimensional sheet of paper. So I'm going to take a point in space over here. It has some distance to the origin, right? That's rho. Now, if I drop that point down into the xy plane, I can look at the shadow of that line here that I labeled rho in the xy plane. This is a 90-degree angle here. This angle here, that's phi. Okay, now things are getting a little crowded already. Okay, so that's rho. This angle is phi. It looks like this. It's a O with a line through it. Sometimes people draw a cursive phi and it looks like this. So that's phi. So I think I can actually see just from that how to get z. I can see the relationship between z and these coordinates, okay? Because if I project in this direction to the z-axis, I will get my z coordinate, right? And just by using a little bit of trig, we know that this distance, the adjacent side to this right triangle, is the hypotenuse, which in this case is rho, times the cosine of this angle, phi. So we've already got one of our equations. We know that z is equal to rho cosine phi. That's one of the three equations we're going to have for x, y, z. All right, and that one just comes from a little bit of trig here, realizing that this is a right triangle with hypotenuse rho and angle phi. All right, so that one's the easiest. Now, how do I get x and y? Well, we have to go down to the xy plane. All right, so now project this thing down into the xy plane, and let's look at this line here. If this distance is rho, then what's this distance? Well, that's the same as this distance up here. Well, that's rho sine phi. All right, so this distance down here is rho sine phi. That's that distance. All right, so now let's find out what x is. So what we're going to do is we're going to project onto the x-axis. So that's our x coordinate right there. Well, we have another triangle. This we projected directly into the x-axis. That's a 90-degree angle right there. The hypotenuse is rho sine phi. So if we can get this angle, we can write down what x is. But we know what this angle is. That's how theta is defined. This angle here, things are getting very crowded already. Sorry about that. This angle is theta. Right? That was how theta was defined in spherical coordinates. So if I take the hypotenuse times the cosine of theta, I will get the length of the adjacent side. So it's rho sine phi times cosine theta gives me x. So that's my other equation. Rho sine. Let me write it another way. We usually write it with the cosine theta first. Rho cosine theta sine phi. Doesn't matter, but that's conventional how they write it in the book anyway. So I'm going to do it the same way. Okay, so this is the x coordinate. What about y? Well, we just do the same thing. To get the y, I project onto the y-axis. Because I'm projecting directly onto it, I get a 90-degree angle here. This is my hypotenuse, right? And I'm trying to find the length of this side. I'm trying to find what this value is. Well, the length of this is the same as the length of this. So let's just look at this triangle. My hypotenuse is rho sine phi. So rho sine phi times sine theta will give me this side. So let me write it this way. Rho sine theta sine phi is my equation for y. All right, so we did it. We got the equations that relate Cartesian to spherical coordinates here. Okay? So what we need to do next is we need to talk about that volume element. Right? Volume element, dV. What is that going to look like? All right, well, let me go back to the computer. Hopefully it works okay this time. So we will go here. I got a little picture of the volume element, which this is even harder to draw, so I hope this works. Oh boy. Okay, let me go this way. Seems like reloading those tabs is what's giving it a hard time. I don't know. I have no idea why. Get out of here, tabs. Wow. Yeah, the video's not frozen. My computer's looks like it's a little bit stuck here. Okay, good. Okay. So here we have here we have a picture of the volume element, all right? I have to move some of the zoom controls around here, get them out of the way, okay. So what we're gonna do is we're gonna look at a little change in phi, all right? So let me see, which one is that? That's this. So the angle in this direction is the phi, right? So if I look at a small change in phi, I'm just imagine this distance being very small, this angle here being very small. And then I'll look at a small change in theta. So that imagine this angle in this direction being very small. All right, and then I'm going to look at a small change in rho. That's going to be this distance, very small. All right, so they're not so small in this picture, but what I'm getting is I'm getting a wedge, looks like this. Okay, can you see this thing spinning around? I hope you can. Sometimes when I push something to full screen, it doesn't share correctly, so I hope you're seeing what I'm seeing here. If not, I'll post it in a separate video, or post a link to this thing. So we want to find the volume of this, all right? So the distance in this direction is a small change in rho, so it's a d rho, okay? So that's going to be part of it. Then the distance in this direction is just like in, well, let's do this direction here. That's the theta. D theta, remember, just like in polar coordinates, we do not d theta, but we do r d theta. But in here, in this case, we don't have r, we have rho. So this distance is going to be rho d theta. And then this distance here in this direction is, well, there's a d phi involved, okay? But we have to get, there's something more to this. Let me, oh, okay, yeah. This distance is rho d phi. All right, this is d rho. It's the theta thing that we have to be a little bit careful about. Let me bring this to the paper and I'll show you what we have to worry about here. Okay, so let's go back to the paper. So what I had here in that picture was this wedge-shaped object, right? And that's not the best picture. Let me try to do that like this. Okay, so we have our coordinate system down here. So these lines all converge at the origin. We said that this distance here is rho d phi. This distance in this direction is d rho, right? And what I'm worried about is what this dimension is down here, or this one over here. We're going to multiply all those together to get our volume element. The thing is, this is not just rho d theta, because d theta lives down in the xy plane. So to get rho d theta is actually what I get when I drop this down and I look at the corresponding arc down here. All right. So this arc down here is rho d theta. I have to lift that up and see what it becomes when I swing it. Actually, it's not when I drop it down, it's when I swing it down. So actually, boy, I wish I had that. This is why I don't like to do this on a sheet of paper. So if I swing this down like this, that's my rho d theta. So I have to swing it back up and see what it becomes, all right? And so how do I do that? Well, no, maybe I was right the first time. Maybe it was when I just drop it down. Let me see. Give me a second. Yeah, I don't think it really matters. I think it is when I just drop it straight down. But the point is, what I have to do is I have to, it's not rho. Okay, up here it's rho, but when I drop it down, what did rho become in the other picture? I'm doing a kind of a bad job explaining this. When I take rho up here and project it down over here, all right, what did it become? What is this line? Right? Rho became rho sine phi. And that's the key point that I'm trying to make here, is that this rho, the distance here, when I look at it down here, becomes rho sine phi. All right, so instead of rho d theta, got a little bit of a mess here. Instead of rho d theta, I'm going to have rho sine phi d theta. And that is how I measure this distance on this thing. And that's because of theta lives in the xy plane, and rho, when you project it down, becomes rho sine theta. I think that's the best way to say this. And so when that's the dimension in this other direction, all right? So that's what I have to include. So I have my three components of the volume element: this, and this, all right? So those are the three things I have to multiply together to get my volume element, okay? So dV is going to be the product of those three circled things, all right? So I'm going to have rho d rho. I'm going to put it in this order: rho times d rho times, oh, no, I'm not. Okay. Okay, rho times rho sine phi. Okay, so that's going to be rho squared sine phi, and then d rho, d theta, d phi. It doesn't matter what order you write them in. I just want to write it down like they have it in the book so that it's consistent. All right, you could mix these up and put them in a different order. It's fine. But basically, the basic idea here is that I just multiplied these things together. Okay. All right. So that's the volume element I have to use in spherical coordinates. Looks a bit yucky, right? Not the prettiest thing in the world, but that's what works. Okay. So so what we're going to do now is we're going to use that to do a triple integral in spherical coordinates. Okay. So our integral is going to be, I got to start saving paper here. So I'll write it down here and then move to another sheet. So I'm going to do the integral of x squared plus y squared plus z squared dv, where R is the region, I'm just going to describe it in words. R is the region above the cone phi equals pi over 4. And we'll talk about why that's a cone in a little bit. And below the sphere, rho equals 2. You know, we keep doing 2 a lot. Let's do rho equal 3. Just to, I don't want to, we did, I don't know. I remember we had 2's appearing a lot in these problems, so I'll just make it a 3. Okay, so this is what we want to do. So, okay. All right, why is phi equals pi over 4 a cone? Well, if I fix phi, let me go back to okay, wait a minute. Oh boy. Okay. computer's getting really kind of choppy here, so I'm always worried it's gonna crash. Okay. Here we are. Okay. So here we are, have the spherical coordinates set up here. If I just fix phi, so here the phi is the angle from the z-axis, right? If I fix phi at, we said pi over 4, so that's, I don't know, a number a little bit less than 1, so let's put it at 0.8 here. That's close enough. Now, if I vary the other coordinates, like theta, look what I get. I just spin around, and I think you can see that that's tracing out kind of a cone shape, right? If I just imagine what gets traced out by that line segment, it's tracing out a cone. It's a fixed angle from the z-axis. And then I'm also imagining that rho is changing too. So I'm getting a cone that, you know, it spans all the way from rho equals 0 all the way out to infinity. So it's like an infinitely extending cone. But because phi is fixed, I've got a definite angle to that cone. If I fix phi at some value, it's definitely tracing out a cone with a particular angle off the z-axis. Okay, so I just wanted to demonstrate that. Okay, so that's why that is why phi equals pi over 4 makes a cone, and then rho equals 3. Well, why does that make a sphere? Well, you're looking at all the points whose distance from the origin is 3. Well, that by definition is a sphere of radius 3. That's what a sphere is. The set of all points equidistant from a given point, right? So that's what we're dealing with here. We're looking at, let me draw a picture. We've got our cone with an angle of pi over 4 in here. And then we got a sphere, but we're looking at only the part of the sphere that lies above the cone. So we're looking at kind of this, I've exaggerated it a little bit so that is a little bit more clear. I got the top of the sphere up here. So the sphere actually goes all the way around, but I'm just looking at the top of the sphere that lies above the cone. All right. So it's kind of like an ice cream cone that we're finding the volume of, or not the volume of, we're integrating this function over. All right. So we're integrating that's the region R. Okay. So just like in cylindrical coordinates, we have to convert this stuff into the spherical coordinates. All right. Well, here is the things that we have to plug in. All right. So let's plug that stuff in here. Now you might be saying, if you're thinking about this a little bit more deeply, you might be realizing there's a very easy way to write this in spherical coordinates. You just use a little bit of your intuition and understanding what x squared plus y squared plus z squared represents. I think you might be able to see the answer already. All right. But I'm going to go through how you plug these in just for completeness, because you will have to do that kind of thing in other problems. All right. But you might want to think about it as we go along. What must this be? You'll see we'll end up with a very simple answer. Okay, so x squared plus y squared plus z squared. Well, remember x was rho cosine theta sine phi. So x squared is going to be rho squared cosine squared theta sine squared phi. Y squared, rho squared sine squared theta sine squared phi. Z squared. Z was rho cosine phi, so z squared is rho squared cosine squared phi. Okay, what happens when I add the first two together? All right, so when I look at just x squared plus y squared, I get this plus this. Notice they both have a sine squared phi in them, and they both have a rho squared, so I can factor that out. The only thing they don't have in common is this part and this part, the cosine squared theta and the sine squared theta. all right? Oh, but this is nice. This is just equal to 1. We know that from trig, right? Pythagorean theorem. So this is just rho squared sine squared phi. Okay? So therefore, what is x squared plus y squared plus z squared? Right? Well, now I'm going to add this to this. Right? So I'm going to have rho squared sine squared phi plus rho squared cosine squared phi. And I can factor out the rho squared. Right? Sine squared phi plus cosine squared phi is equal to 1, right? So this is just rho squared. All right? And you may have been able to realize that from before, like x squared plus y squared plus z squared is just the distance from the origin, which is what rho is, right? But it's the square of the distance from the origin. So that's what rho squared is. So we could have probably intuitively just kind of thought of that without having to go through all these computations. Okay, so that's what our integrand becomes. It just becomes rho squared. X squared plus y squared plus z squared is just rho squared. Now, what does dv become? Well, we wrote that down before. dv was rho squared sine phi d rho d theta d phi, right? So there we have it. Now, we have to put the bounds on our integral, okay? Let's look at the picture. First off, d rho, all right? Well, we're filling in this region, all right? We're going from 0 up until we hit the sphere, right? The sphere had radius 3. So we're going from 0 to 3. What does d theta do? D theta spins us all the way around. We're doing this whole thing, right? So theta goes from 0 to 2 pi. What does phi do? Well, phi starts us up here and then brings us all the way down till we get to the cone, right? How much of an angle is that? Well, it's pi over 4. So phi goes from 0 to pi over 4. All right. So there we have it. We can simplify the integrand here. So really, we're just doing this integral. This thing is just rho to the 4th sine phi, right? So when I anti-differentiate with respect to rho, I get 1/5 rho to the 5 sine phi. And then I'm going to evaluate that from 0 to 3. So, okay, 1/5, 3 to the 5th. So that's just 3 to the 4th. 3 to the 4th is 81, right? So it's 81. When I evaluate it, do that integral, I get 81 sine, yeah, that's right, sine phi. Doing that, just anti-differentiating this from 0 to 3. Okay. Now we do the antiderivative of this thing with respect to theta. Right. Well, there's no theta. This is just all constant with respect to theta. So I just get 2 pi times this. Right. So, okay, 81 times 2 is 162. So 162 pi times sine phi. That's this integral becomes this. Okay. Now, what about this integral here? Well, the antiderivative of sine is negative cosine. Okay, so we have negative 162 pi cosine phi evaluated from 0 to pi over 4. Okay. Okay, so we're going to plug in the pi over 4 for phi. What's cosine of pi over 4? It's square root of 2 over 2. So that is negative 81 root 2 pi. And then when I plug in 0, so that's when I plug in pi over 4, right? Now, what about when I plug in 0? Well, I get minus 162 pi, right? Because cosine of 0 is 1. Right? So cosine of pi over 4 is root 2 over 2. So I just multiplied this by root 2 over 2, and I get this. All right. And so what do I get? I get these two minuses become a plus, so I get 162 minus 81 root 2 pi. I was a little worried a bit into there, thinking I was going to get a negative answer, which can't be the case, right? Because we integrated a non-negative function over a region. We have to get a positive thing, but no, it came out. This number is definitely bigger than this number, so it's going to be positive. So that looks about right. All right. So we found the volume, well, not the volume. We integrated that function over that ice cream cone shape. Okay. Okay. I want to look at one more example. So what I'm going to do is I'm going to take us to our book, and we're going to look at this problem there. So there's one other type of problem. So you should be seeing the textbook now. Well, actually, I guess there are a couple problems here. Examples 5.50 and 5.51. Some problems will just give you an integral like this, and they'll ask you to convert it into cylindrical coordinates. Okay, so they don't tell you what the region is, they just give you the integral right away. And so you're gonna have to look at this thing and convert everything in here, in the case of cylindrical coordinates, to dr, d theta, and dz, or in r and theta and z up here in the bounds. Okay. Now, I'm kind of out of paper, so not kind of out of paper, I'm definitely out of paper. So what I'm gonna do is I'm gonna walk through what the book does, okay, with you. So we'll just go through here. So notice that the outer integral goes from y equals -1 to 1. You can't just directly convert that into theta or r or z, because if you remember the equation, y was r sine theta. It's in terms of two different variables. So you can't just replace this stuff, these values with something in terms of theta or something in terms of r. We actually got to pull this whole thing apart and then kind of reconstruct it a little bit. So what they do is they say the ranges of the variables, they just observe that y goes from -1 to 1. The next integral is with respect to x, that goes from 0 to this, square root of 1 minus y squared. And then the z goes from x squared plus y squared to root x squared plus y squared, okay? So now what you want to do is you want to visualize what this represents, okay? The first two inequalities, they say it describes the right half of a circle of radius 1. Why is that? Well, you should recognize this over here. I'm trying to highlight just the square root and the, okay, I can't. Okay, the square root of 1 minus y squared, right? That you should recognize as the equation of a circle solved for x. Circle of radius 1 solved for x. So that's where they're getting this idea that it's a circle. Now, the fact that x goes from 0 up to there says that it's not just the circle, the perimeter of the circle, it's actually the interior of the circle, but it's only the right half of the circle because x is always greater than or equal to 0. Right? So we're only getting the right half of a circle. That's what we can tell from this. Radius 1 because this is a 1 here. And from that, you can piece apart what r and theta have to be, because now you have a circle. So a circle's nicely described in terms of r and theta. If the circle is a radius 1, that means r goes from 0 to 1. And so that's what they write down here. If it's the right half of a circle, that means that theta can only go from negative pi over 2 to pi over 2. That gives you the right half of the Cartesian plane. Right? If you go past pi over 2, you're to the left of the y-axis. Right? So just looking at this tells us this stuff here. Right? All right. The fact that y goes from -1 to 1 is actually also encoded in this, right? Because if you think about a circle, the right half of a circle of radius 1, it will go from as low as y equals -1 to y equals +1. So actually, this is also encoded in this right here. Now we look at the limits for z. Z is bounded below by x squared plus y squared, but we should recognize that that's the same as r squared, right? Just by using those formulas for x and y and polar coordinates, or cylindrical coordinates, same equations, right? And then the square root of x squared plus y squared is just r. Right? So that's what they've written down here. They've pieced this apart. So now they're going to put that back together, all right? We know that theta goes from negative pi over 2 to pi over 2. So they did the outer integral with respect to theta, and they put these bounds in. R goes from 0 to 1. So they did the next innermost integral with respect to r, and they did it from 0 to 1. And then finally, z goes from r squared to r. Because this one depends on r, it needs to be more interior than the r integral. All right, that's why they put it all the way to the inside. So the innermost integral, they said z went from r squared to r. Remember, you need to resolve this integral before you get to this variable, right? Because it's got that variable in its bounds. So it's very important that this integral came before the r integral. That's very important. And that's how you'd rewrite this integral. They don't work it out. If you wanted to work it out, you could go through the steps and try to do that. But the important part here, for the sake of this example, is just showing you how to do this. So it's not just a matter of simply substituting in place of these variables. You actually have to think about what the region represents and then rewrite it in terms of the new variables. Okay, you're gonna have to, so I recommend drawing a picture here and thinking about the picture. And they do the same thing for spherical in this next example. So they want you to convert this into spherical coordinates, okay? So they piece apart the ranges of these variables. They observe that y, the outermost integral, goes from 0 to 3, right? That's this right here. Then they observe that the x, the second integral, goes from 0 to root 9 minus y squared. Then they observe that z goes from this stuff between here and here. The first two ranges of variables describe a quarter disk in the first quadrant of the xy plane. Why is that a quarter disk? Well, look at the second inequality. This, just like in the example above, this is a circle of radius 3 instead of a circle of radius 1 in the previous example. And so x is going all the way from the y-axis up until it hits that circle of radius 3. But y is only going from 0 to 3. So we're actually only looking what's above the x-axis too. So instead of getting a half of a circle here, we're getting the upper right quarter of a circle of radius 3. So that's what these two inequalities tell us, that we're in the upper right quarter of a circle of radius 3. Okay? So that means we know that theta starts at 0 and goes to pi over 2. That gets us exactly a quarter of the way around the circle. It also tells us what r does. They don't say it yet here, but I can see here that r, oh, we're not doing r, we're doing spherical. Okay, well, okay, I'll hold off on that. We're doing spherical coordinates. There's no r, there's a rho instead. Now let's look at these next equations down here. This lower bound is the upper half of a cone, right? If you take x squared plus y squared, take the square root, that gives you a cone, right? And same, oh, not the same thing. This one over here, if you take 18 minus x squared minus y squared, you should recognize that being the equation of a sphere. So we're between a cone and a sphere. That's exactly like the problem that we just finished, the ice cream cone looking thing. It's one of those, right? So it's below the sphere and it's below the sphere and above the cone. So just like the example we did on the sheet of paper, right? We worked it out, same kind of shape, different radius, but it's the same idea, all right? So setting it up the same way, you know that rho goes from 0 out until it gets to the radius of the sphere, which in this case is root 18. Phi, just like we had before, goes from 0 up until we get hit that cone, right? And that cone, they actually find the angle corresponding to this cone. They work it out down here, right? So they go ahead and they replace this thing with r squared in here, and then they square both sides. They say x squared plus y squared is the same as r squared. I guess they're temporarily using cylindrical coordinates. They work it out. They find out what where the cone and the sphere intersect, right? They find out the value of z, and they use that to find the angle that phi has to be. And just like our cone in our last example, it comes up to be pi over 4. And so by deconstructing it in that way and then putting it back together, just like we set up our last integral, so look at the last example that we did in the video on the sheet of paper, it's the same shape, so we set up these bounds in exactly the same way. And in fact, this should look pretty familiar. We got a rho to the 4th, I believe, in there as well, right? Or did we? Oh yeah, they're doing almost the same integral. Look at this. It's x squared plus y squared plus z squared. That's why okay, I'm surprised okay, that's why. Yeah, so it's almost the same as it's almost exactly the same as the problem we worked out before, right? It's just got a sphere of a different radius, okay? So that's triple integrals in cylindrical and spherical coordinates. Are there any questions? Okay, I'm not hearing anything. So, oh, good. Good. It's right around 11:30, so I think it's time to stop. I have to have time to encode this video before my next class. So I'm going to end the meeting and make sure you work on the homework. I'm going to post a new one for the spherical and cylindrical coordinates. Won't be due this Sunday. Will be due probably Sunday of next week. But it'd be really good if you get an early start on that so you can ask questions about it next week. Okay. So we'll meet again on Tuesday, Wednesday, and Thursday next week. Same meeting number, same link, same password. If that changes, I'll let you know. But as far as I'm aware, it's going to be all the same information. Okay. I don't remember let me quickly look. What's due this Sunday? Yeah, I'm not going to add anything new. So yeah, 5.3 and 5.4 are the only things that are due this Sunday. Any questions? Okay, so have a good weekend. Stay well. And I'll see you on Tuesday. Okay. Goodbye. Thank you. Thanks for coming and participating.